Hello everyone, my name is Meng Wu, and I'm a master student in the ECE department here at Northwestern. Today, I'll be presenting my final project for the Scientific Machine Learning course. My research focuses on evaluating how well advanced scientific machine learning architectures, specifically neural ODEs and physics-informed neural networks, can learn and predict the chaotic dynamics of the Lorenz system. Now, let me briefly walk you through the structure of my presentation. I'll start by introducing what the problem is, so we have a clear understanding of the task we are trying to solve. Then I'll explain why this problem is important and review what existing approaches have already been done in this area. After that, I'll move on to what we propose in this project, followed by a detailed explanation of the methodology. Next, I'll present the results from three different approaches. First, the baseline MLP, then the physics-informed neural network, and finally the neural ODE model, so we can compare their performance. After reviewing the results, I'll discuss some key challenges and limitations we observed during the project. Finally, I'll wrap up with the conclusion and outline some possible future work. Let's get started. To understand the problem, we first need to look at the Lorenz system. This system is a classic mathematical model for atmospheric convection and is the hallmark of chaotic dynamics. The core issue with chaotic systems is their extreme sensitivity to initial conditions, commonly known as the butterfly effect. If two trajectories start incredibly close to one another, they will still diverge exponentially over time. This makes long-term forecasting notoriously difficult. So why does this matter? Being able to predict chaotic systems has massive implications for weather forecasting, fluid dynamics, and engineering. Currently, we rely on traditional numerical methods like the Ranch-Kutta or RK4 family of solvers. While highly accurate in the short term, these solvers suffer from rapid error accumulation during long-term trajectory prediction. On the other hand, standard deep learning architectures like multi-layer perceptrons have been used to learn time series data. They completely ignore the underlying physical laws and continuous time nature of the system. This brings us to our proposed solution. We investigate the efficacy of scientific machine learning, which bridges the gap between pure data and pure physics. We evaluate two specific models. First, neural ordinary differential equations, which parameterize the derivative of the hidden state and treat the network forward path as a continuous initial value problem. Second, physics-informed neural networks, or PINNs, which embed the governing differential equations directly into the loss function to penalize non-physical predictions. For our methodology, we generated our ground truth dataset using the standard chaotic parameters for the Lorenz system. Sigma equals 10, rho is 28, and beta is 8/3. We simulated the system over a time domain of 20 seconds with a step size of 0.01, giving us 2,000 discrete data points generated via an RK45 solver. We then trained our ML models on a subset of this data to test their ability to autonomously forecast the future trajectory given the starting condition. To do this, we evaluated two distinct scientific machine learning architectures. First, let's look at the physics-informed neural network. The core idea here is to rethink the loss function. As you can see on the slide, instead of just minimizing the error between our predictions and the training data, which is the L data term, we introduce a second term, the physics penalty, or L physics. We use automatic differentiation to calculate the derivatives of our networked outputs and plug them directly into the Lorenz equations. If the network predicts a trajectory that violates these physical laws, the loss function heavily penalizes it. The lambda parameter simply acts as a weight to decide how strictly we want to enforce those rules. Next, we use the neural ODE architecture, which takes a completely different approach. Standard neural networks learn discrete step-by-step mappings. A neural ODE, however, uses the neural network to parameterize the continuous derivative of the hidden state itself. You can think of it as replacing the right-hand side of a traditional differential equation with a neural network. We then use a black box ODE solver to integrate this network forward in time. This turns the entire forward path of the model into a solution of a continuous initial value problem. I will spare you the fine-tuning details of these architectures here, as all the hyperparameters, loss weighting strategies, and solver implementations are fully documented in the project's GitHub repository. Moving to results, let's first look at our baseline, the multi-layer perceptron. We trained the MLP to learn the discrete step-to-step mapping. While it achieved a low mean squared error during single-step training, if you look at the 3D plot on the screen, you can see that it failed entirely during autoregressive rollout. The blue lines are the true chaotic butterfly, but our MLP prediction, the red dashed line, rapidly diverges and collapses into a tiny, non-physical orbit. The reason it crashes into this micro-orbit is that naive feed-forward architectures completely lack the temporal, continuous inductive bias required to understand dynamical systems. They treat data as independent snapshots rather than a continuous flow in time. Next, we applied the physics-informed neural network, where we added the physical equations directly to the loss function. Look closely at the graph. The green dashed line represents the training region. Here, the model perfectly captures the dynamics and interpolates the data flawlessly. But notice what happens right after the black dot, which marks the prediction start point. During the extrapolation phase, represented by the red solid line, it rapidly shoots off and diverges from the true attractor. So what we learn here is a key limitation. While physical residuals force the model to respect the governing equations, relying on them alone without continuous data assimilation is simply insufficient for the long-term forecasting of highly sensitive chaotic systems. Finally, we tested the neural ODE framework. By utilizing an adjoint ODE solver, this model demonstrated the most robust macroscopic behavior. Notice the orange line on the right. Unlike the MLP that completely crashed, the neural ODE successfully restricts its predictions to the correct physical manifold. It actually stays on the butterfly, however, it still faces a major hurdle. If you trace the orange line, you'll see that instead of randomly switching back and forth between the two lobes like a true chaotic system, it gets stuck tracing just one lobe over and over. It collapses into a stable limit cycle. The main culprit here is the mean squared error loss function. In a chaotic system, if the model is just slightly late in crossing over to the other lobe, MSE imposes a severe penalty. To minimize this catastrophic penalty, the network essentially plays it safe. It learns a conservative dynamic, the limit cycle, rather than risking the true aperiodic switching behavior. This brings us to the main discussion of our findings. While embedding continuous time dynamics or physical priors significantly improves short-term interpolation compared to naive deep learning, long-term extrapolation remains a formidable challenge. The root cause of this limitation stems directly from the objective function. As we observed with the neural ODE, standard MSE loss severely penalizes the model when even a small temporal phase shift occurs during lobe transitions. To minimize this catastrophic penalty, the network learns a safe conservative dynamic, which manifests as the stable limit cycle we just saw. Ultimately, this reveals a fundamental misalignment. Pointwise loss metrics such as MSE are simply mismatched with the topological objectives of predicting chaotic dynamics. To conclude, if you want to solve chaotic systems with machine learning, future work must transition away from simple trajectory matching towards invariant measure matching. Exploring chaos-specific loss functions or employing curriculum learning strategies like time marching are essential next steps. This project clearly demonstrated both the power of scientific machine learning in capturing physical manifolds and the inherent limitations we still need to overcome regarding long-term chaotic divergence. Thank you for your time. The full code base, including all hyperparameters and software implementations, is available on my GitHub repository. Have a great day.